Hey there, Calc folks, back here with another quick video where we are, we're wrapping up integration techniques, right? We're kind of getting to the end of our study of integration and getting into some of these advanced techniques. We're at the end of integration. I always like to make sure that it is clear with students that, first of all, not every function is integrable using the methods that we've discussed up to this point. Unlike the derivative, most functions we have techniques for finding derivatives, right? We have developed numerous techniques for finding the derivative of a function, and we have so many techniques that we can likely find a derivative for just about any case. I don't think of too many functions where the derivative calculation is obscure. All right. Whereas in terms of integration, it's not so easy. It is not so easy, right? Not every single function we encounter necessarily is integrable with the methods that we've developed up to this point. All right. So what does that mean? Well, that means that not every function you can find the antiderivative for using our fundamental techniques or the techniques we've developed up to this point. And not every definite integral can be calculated, right? Exactly. Not every single function can we find the area trapped between it and the x-axis over some interval from a to b, right? Using the process of the antiderivative, right? Evaluating that antiderivative across those bounds. Finding the antiderivative is going to be difficult, right? Or if not impossible. So, what we develop as an alternative, right? What we develop as an alternative, folks, are some approximation techniques. And these approximation techniques are wrapped up in what we call essentially numerical integration, right? Where we are using our Riemann sum understanding, right, of a definite integral calculation to actually go about approximating the value of a definite integral, right? Especially in the cases where our function is not integrable. And that is what we end up developing in the end of our study here, folks, is we're going to develop a few numerical integration techniques. I do plan to give descriptions for the midpoint rule, trapezoid rule, and I'm hoping Simpson's rule. We're going to have to look at time here this semester. I may or may not be able to get into Simpson's rule. But I will at least talk about numerical integration using midpoint rule and numerical integration using trapezoid rule. All right? And that's what I'm going to present in this set of notes. I am going to look at midpoint rule here to begin with. Right? And we've learned a little bit about midpoint rule already. Take note. We may have done some midpoint Riemann sum calculations back in, our introduction to the definite integral calculation back in Calc 1. Right back at the beginning of that study, right? Where, if you recall, back at the beginning of that study, we did develop the understanding that a definite integral calculation is just a limit calculation applied to a summation, where this summation is known as a Riemann summation, right? In this Riemann summation, we are subdividing our interval from a to b into n subintervals, right? Where the width of the case subinterval is given by delta x, this quantity b minus a divided by n, and x sub k represents a value in the case subinterval. All right? We did develop this idea back at the beginning of calculus, right? Or back in our calculus study at the beginning of integration. Right? This is how we formally understand the integration process. And in fact, this is what we studied at the beginning of even this semester when we were looking at application of integration. Not only was it the development of the formulas, but it was the formulas that were presented that involve integration. It was their development that came from a limit of a Riemann sum understanding, right? This process known as integration. Well, what this result does imply, folks, right, is that we can use a summation to approximate a definite integral calculation. Absent the limit in our definite integral understanding, all we have left then is our summation, where our summation from k equals 1 to n could be used as an approximation of our definite integral calculation. Right? And if you remember, this is how we began developing the understanding of a definite integral. As we started by approximating its area using a Riemann sum, right? And then applied a limit to make it exact. Well, we're taking a step back and taking the limit off and going back to the summation and considering that as an approximation. Okay? With this approximation growing more precise as n heads to infinity, right? As n approaches infinity, this approximation will become more precise. The limit as n heads to infinity will be the definite integral value, right? Well, you can increase that precision then in our summation by letting n head off towards infinity. Now, for a given value of a function and choice of x sub k, the value of n and value of n, right? The approximation will contain a particular amount of error caused by these choices. One way to potentially decrease this error is choosing a value of x sub k given by the midpoint of the k subinterval from a to b. Typically, when we have developed Riemann summations in the past, we have developed them using left and right Riemann summations. Whereas if we go with a midpoint summation, that is one way to go about potentially decreasing the error in your calculation. All right? Remember, in the case of the midpoint, it's the value of x sub k that differs. Right? That is very specific. And in the case of the midpoint, x sub k is calculated as follows. It is equal to a plus the quantity k minus 1/2 times delta x. Where if we know delta x and we know a, this statement here can be simplified for the value of x sub k. Let's consider an example here. If I scroll down, we might consider a case where we already know how to calculate the definite integral, just so we can check precision here. Excuse me. Consider approximating the definite integral from 1 to 9 for the quantity x cubed dx using the midpoint value for x sub k, right? And the case for n equal to 4 subintervals, right? In this case, for n equal to 4 subintervals, delta x would be equal to 2 in value. You would take b minus a would be 9 minus 1, developing from our bounds on our definite integral. Right? 9 minus 1 divided by our number of subintervals 4 would tell us our width of each subinterval would be 2. And then our value of x sub k would come from a, which is 1, plus the quantity k minus 1/2 times delta x, which is the value of 2. Again, the value at 2. Distributing the 2 throughout that quantity will produce 1 plus 2k minus 1 in this case, which is just equal to 2 times k in value. Right? The midpoint here is 2 times k in value, where for 4 subintervals, right, the midpoints at those 4 subintervals would be at 2, 4, 6, and 8. The value of f at x sub 1, x sub 2, x sub 3, and x sub 4 seen in the above calculation, right, of the midpoint formula. The values of f sub k seen up here, right, will be at f of 1, f at x sub 1, f of x sub 2, f of x sub 3, f of x sub 4, which would then be at, like we said, f at 2, f of 4, f of 6, and f of 8 respectively, using the value of 2k, right? K is 1, x sub k is 2, k is 2, x sub k is 4, k is 3, x sub k is 6, k is 4, x sub k is 8, because x sub k is always 2 times k. Where if we now evaluate our function, and maybe I should put that here. So for f of x equal to x squared, the values of f at, let's say it this way, the values of f at x sub k found in the summation from k equals 1 to 4 of f at x sub k times delta x, comma, are given as follows. Let's be specific there. I want to add that line. All right. These values seen down here. What we are finding are these values of f sub x sub k found in this summation calculation. This summation we are going to approximate using n subintervals. And what we might say here is consider approximating, what we are considering here is approximating this integral, right? Using the summation from k equals 1 to 4 for f of x sub k times delta x in value. Right. This is what we're considering. Right. Using, right, and we could, yeah, we'll say it that way. All right. If we assemble that summation, hopefully I didn't get too redundant here. I don't think I did. All right. Using the midpoint, an approximation of the integral using n equal to 4 subintervals is as we had just stated up above, which is going to come from this calculation here, f at x sub 1 times delta x plus f of x sub 2 times delta x, all the way up to f of x sub 4 times delta x, which is just going to be the values we've defined up above here, 8, 64, 216, and 512, multiplied by 2 and summed together, which does give us these terms in our summation, where when summed yield the value of 1600. And specifically we might say here, because we are looking just at this as a net area calculation, would be units squared. And thus, the approximate definite integration here, in this case, would be 1600 units squared. Right. Using this midpoint calculation and n equal to 4 sub-intervals, where here in this illustration, I am showing you what we are actually calculating the area of. Keep in mind, in a Riemann summation, to calculate this area trapped between this curve from A to B, we are using these rectangles area, where we have subdivided from 1 to n, or sorry, 1 to 9 into n equal to 4 subintervals. Here's our 4 subintervals, each of width 2, where we are using the midpoint of the subintervals in our approximation. And we get a very, very close approximation here, folks. Notice where the heights of these rectangles occur at is at the midpoint, right? Is at the midpoint of these intervals. Right? The amount of over-approximation is equivalent to how much we're really under-approximating, and we get a very good sense of balance here, right, in terms of what would be the area trapped within that subinterval. Right? We're only off by just a slight amount. How much in total we might consider is our error. We actually know in this case, if we were to calculate the true definite integral, it would be 1,640 units in value, units squared in value, indicating that the absolute error is only 40 units, 40 units squared. And the relative error, right, is about 2.44%. Very, very small amount of error in this approximation. And notice we are only using 4 intervals. Increase our number of intervals, and that error is going to decrease, right, in our calculation here. All right. Let's do one more example. This certainly becomes more definitive, right? More exact, right? Increasing our number of subintervals. And then likewise, this is very good technique for the case where we can't find an antiderivative for a function in a definite integral calculation. Consider this case here. Consider approximating the integral from a to b, or -1 to 1, for the cosine of x squared dx using n equal to 30 subintervals and the midpoint rule. The following would be an illustration of our calculation. Here we have this curve, the cosine of x squared, and we want to find the area trapped between it and the x-axis from -1 to 1 in value. Now, overall, you can see that that does fit into a rectangle that is, no bigger than 2 units squared. So we are looking for something smaller than 2 units squared. That should be obvious here. But how big exactly? Or let's get a closer approximation. Using a midpoint formula and 30 subintervals, delta x is going to be equal to 1/15. B minus a is 2 divided by 30. This length is 2 units long divided into 30 subintervals, means each of our subintervals is going to be 1/15 of a unit in length. And that is true for each of these lengths, right? Each of these subintervals. X sub k then is going to be a plus k minus 1/2 times delta x, which does simplify into -30 1/30 plus 1/15 k. Implying that if we want to calculate this definite integral calculation seen here, it can be approximated using this summation here. We can just evaluate our function at those values of x sub k. And multiply it by the value of delta x. Now, I do think I have a small error in here. Let me double check this. I'm going to pause this just for a minute and double check this error. Now, I do have a bit of an error here. I should have in here, this is delta x, 1/15, times f at x sub k. Now, I forgot to have the square. I got to go back and put that square in there, which does make me question this. I don't think this is right. We got to go figure out what that actually calculates out to. And we could do this by hand. We don't want to do this by hand, right? What we might go rely upon is our calculator here, folks. Let me bring up the calculator to do this calculation. Hopefully this doesn't crash my program here. Let's open up the calculator. I'll bring this over here. Let's put together this calculation for our summation seen here. And the way we do this, folks, okay, I should be able to switch back and forth right here. Okay, there we go. The way we're going to do this is we are going to sum a sequence. This is going to be sums of a sequence that goes from 1 to 30. All right, this being our sequence, and we are going to do this on our calculator. All right. If you recall how to do a sequence on your calculator, it's all going to happen underneath your list menu. If you go second, list, let's see if I can get it to go. Oh, no wonder. Got to be actually clicking on the calculator. Clicking on my program here. So we go second list, scroll over to math, and you will see the sum option. So we're going to go down and grab sum. And then we're going to go back under second list and go over to ops, and you'll see sequence. So we'll go down and grab sequence. And we're going to sum a sequence here. What's the sequence? Here's the argument of our sequence. We're going to put that in. Right? This value seen here is going to be the argument of our sequence. We're going to want to put that into our calculator. So that is going to be 1/15 times the cosine of the argument negative 31/30 plus 1/15 times our variable. Now we're going to use x instead of k here, folks, in the summation, but that is going to play the role of our variable of summation, where that quantity is going to be squared inside of our cosine. Yes. Oh, and I missed my squared. I put the caret, didn't put the square. So squared inside of our cosine. We are going to sum this over values of the variable x, starting at 1 and going up to the value of 30. Right. And the sequence and the summation of that terms in that sequence. Now if I hit enter, that would be our calculation. So I was a little off. It's 1.097, 1.8097 in value. And that's performing the calculation on our calculator. Remember, those operations are underneath your list menu. Under math, you will find the sum. Start there, and then come back and grab the sequence under the ops menu. All right. And in the end, you will get, when you plug all that in, right, the argument of your calculation, your sequence, summing from x equal to, summing over values of x from 1 to 30, right, will give us about 1.8097 in value, folks. So this down here is about 1.8097 in value. And let's get that in there correctly. Units squared. Right. Units squared as a net area. Now again, we were expecting something less than 2 units, and that certainly is less than 2 units, folks. That fits. That fits into this space. Now notice the scaling of the space is a little inaccurate. I could have probably give a little bit better aspect ratio here, folks. The scaling is not. This is 0 to 1. This is 0 to 1. So it's a little out of scale. But what's left out of there is just a little less than 0.2 in value. Right? A fifth of a unit. Right? But this is approximating this definite integral calculation seen down here for the cosine of x squared. Right? Using n equal to 30 subintervals and the midpoint in our calculation. Right? Midpoint rule, folks. All of these rules are going to involve some summation. They all can be done on your calculators as I have illustrated. Right? Sum a sequence on your calculator and you can handle those cases that are a little more than the case for n equal to 4 or 8 subintervals. To do 30 subintervals or 60 subintervals or 100 subintervals, you're going to have to use a computer algebra system or a calculator, a powerful calculator, to do those calculations. All right. But with that said, folks, I hope you're all doing well. I do have another technique we're going to look at in our next set, numerical integration, trapezoid rule. Right, where we're going to see a very similar approximation technique using a summation. Right? However, the shapes in our regions are not going to be rectangular, as we had seen back here in the midpoint rule. The shapes of our regions are going to be trapezoidal. Right? We're going to use trapezoids to approximate these regions. Right? Essentially connecting dots at the endpoints, right, in these regions. I realize you can't see any of that now. But yeah, that is where we're coming back to, folks. Instead of using rectangles in our calculation, we're going to be using trapezoids to approximate these regions, which will give us an even better approximation. Right? So we're going to come back and see that in the next lecture set. With that said, I hope you're all doing well, and I will see you in the next video.